Welcome to the video Basics Sampling Concept. We start this video with a simple audio example, a 400 Hz sinusoidal signal, which sounds as follows. Now let's see what happens with this continuous time 400 Hz sinusoidal signal when we sample with an ideal C to D converter, which runs at a sample rate sampling frequency of Fs is 1 over Ts is 2000 samples a second, or Hertz. The result of this sampling process is a discrete time signal, which is a set of numbers denoted by xn that can be found by evaluating the continuous time signal x of t at time instances t is n times Ts. Thus the output of the C to D converter is a set of numbers which can be stored on a computer. Usually, we represent this set of numbers in a graph, from which the relation between the continuous time signal and the discrete time samples is clearly visible. The ideal D-to-C converter converts the discrete time samples back to the continuous time signal, and the result is again a 400 Hz continuous time sinusoidal signal. Now we use a continuous time chirp signal as input from the same cascading of an ideal C to D and D to C converter. A chirp signal is a signal from which the frequency increases with time, and it sounds as follows. This chirp signal is first converted to the discrete time and after that the continuous time again, without applying any operation to the samples in the discrete time domain. The resulting continuous time output signal sounds as follows. From this example, it's clear that during the conversion process, the original continuous time input signal is manipulated in one way or the other. This manipulation is called aliasing and can be explained as follows. Let's start again with the continuous time 400 Hz sinusoidal signal. When sampling the signal with 2000 samples a second, we obtain the numbers which are shown in the graph. When starting with the 2400 Hz sinusoidal signal and sampling again with the same sampling rate of 2000 samples a second, we obtain the following numbers, which are also denoted in the plot. These numbers are the same as the numbers that we obtained by sampling the 400 Hz signal with the same sampling frequency of 2000 samples a second. The main reason for this is that the cosine function in the discrete time domain is periodic with 2 pi, which implies that cosine 2.4 pi n is equal to cosine 0.4 pi n. So we can conclude that there is no unique representation in the discrete time domain for a continuous time signal. This uniqueness issue results into the following implication when converting the discrete time signal samples back into the continuous time signal, since the same set of samples can be converted to the 400 Hz signal or to the 2400 Hz signal. This uniqueness issue has to be solved. For this, we will first give a frequency domain interpretation of the uniqueness issue. Let's start again with a simple sinusoidal continuous time signal x of t, from which the absolute frequency is given by omega is 2 pi f, with omega in radians per second and frequency f in hertz. For the conversion to the discrete time domain, we use an ideal C to D converter, which runs at a sample rate of Fs is 1 over Ts samples a second or Hertz. In this case, we obtain a mathematical expression for the discrete time samples x of n by substituting t is n times Ts in the expression of x of t, which results in xn is cosine theta n, in which theta is a dimensionless frequency in radians. From this, it follows that the relation between the discrete time domain dimensionless frequency theta and the continuous time absolute frequency omega, or f, is given by theta is omega ts is 2 pi f divided by fs. Now let's see how this works for the 400 and 2400 Hz sinusoidals. As a first step, we use Euler to write the 400 Hz sinusoidal signal as a sum of two phasors, which can be represented in a spectral plot with two bars. When sampling at the sampling frequency fs is 2000 samples a second, we can evaluate the relative frequency, which results in theta is 0.4 pi. In other words, the discrete time signal samples can be expressed by xn is cosine 0.4 pi n, or as a sum of discrete time phasors. These phasors can be depicted in a spectral plot from which the horizontal axis represents the relative frequency theta. The same steps for the 2400 Hz sinusoidal are as follows. The discrete time phasors of plus or minus 2.4 pi can both be multiplied by 1. And the number 1 can be represented as a complex number e to the power, plus or minus, j times 2 pi n. Combining the complex exponents results into the two new discrete time phasor frequencies plus and minus 0.4 pi, which can be represented in the spectral plot. When using the relation between the relative and absolute frequency, it follows that the relative frequency theta is 0.4 pi matches with the absolute frequency of f is 400 Hz. Thus both frequencies of 400 and 2400 Hz results in the same sequence of samples x of n. By adding or subtracting 2 pi, we have mapped in the discrete time domain the frequencies plus or minus 2.4 pi into the interval plus or minus pi. In a similar way, by adding or subtracting an integer numbers times 2 pi, we can map any frequency into this interval of width 2 pi, which is a so-called fundamental interval, abbreviated as Fi. In other words, there is only one fundamental interval of width 2 pi, which represents in a unique way frequencies in the discrete time domain spectral plot. Usually this fundamental interval is chosen in the range minus up to plus pi. By using the relation between the relative and absolute frequencies, it follows that the fundamental interval boundaries of plus or minus pi match with the absolute frequencies f is plus or minus 1000 Hz, which is equal to half the sampling frequency fs over 2. Concluding, it follows that only continuous time absolute frequencies f up to maximal fs over 2 are mapped in a unique way into relative frequencies theta, which are inside the fundamental interval plus and minus pi. This observation is used in the D-to-C converter by producing continuous time signals which contain only frequencies up to maximal half the sampling frequency. This is done by mapping all intermediate frequencies of the discrete time signal into continuous time signal frequencies which will not exceed fs over 2. With this knowledge we are able to explain the effect that we obtained when converting a chirp signal into the cascading of a C to D and D to C converter, both running at a sample rate of 2000 samples a second, and this explanation is as follows. The continuous time input signal can have any frequency, while the frequencies of the resulting continuous time output signal are restricted to half the sampling frequency, which equals 2000 divided by 2 is 1000 Hz for this example. Thus, if the input signal becomes larger than 1000 Hz, the intermediate discrete time frequency will be mapped back into an output frequency which is in the range in between 0 and 1000 Hz. Even in case the input frequency grows higher and higher, the intermediate discrete time frequency will always be mapped back into an output frequency in the range in between 0 and 1000 Hz. This mapping back into another frequency is called aliasing, and there will be no aliasing when all the input frequencies are below half the sampling frequency fs over 2, which is inside the fundamental interval. This results into the following basic sampling theorem, which defines the minimum sample rate that we need if we want to sample a continuous time signal without obtaining the aliasing effect. This theorem goes as follows. When a continuous time input signal x of t contains frequencies which are all below a maximum frequency fmax, we can construct via a D-to-C converter this continuous time signal x of t without aliasing by its discrete time samples. When these samples are obtained via a C to D converter, which runs at a sample rate fs, which is greater than 2 times the maximum frequency fmax. If we sample at a rate which is too low, we obtain aliasing. The following example shows what happens if an audio signal is not sampled according to this sampling theorem. The original continuous time audio signal sounds as follows. When using a sampling rate lower than twice the maximum frequency, we obtain the following aliased audio signal, from which we clearly can hear that higher frequencies are mapped back into lower frequencies. This ends the video about basic sampling. In a follow-up video we will explain in concept how a continuous time signal x of t can be reconstructed from the discrete time signal samples x of n. Thank you for your attention.